we shall solve some questions related to three-phase AC circuits. In this first question, we have a star-connected three-phase supply, balanced supply. The phase voltages are given V1, V2 and V3. Let us put bars above V1, V2 and V3 to indicate complex numbers or phasor values. And here we have a star connected load, unbalanced load, and this current is I, which we have to find out. Let me call this capital I bar to indicate the phasor value. How to solve this? So let us first consider this point at the reference potential. Then this point is at V1, this is at V2, and this is at V3. Then this point is directly connected to V3, so this potential is also V3. Then the current here, let me call I1, will be given by V1 minus V3 divided by minus J, V1 minus V3 divided by minus J. Similarly, the current here I2 is given by V2 minus V3 divided by J. So I2 is V2 minus V3 divided by J. And then this current I will be equal to minus of I1 plus I2. Okay, according to the KCL at this node. Then to calculate the value of this current I, we may use a phasor diagram. Let us draw a phasor diagram. Suppose this is V1 at an angle of 0 degree. This is V2 at an angle of minus 120 degree, and this is V3 at an angle of plus 120 degree. Then I1 is V1 minus V3 by J. Now V1 minus V3 will be this phasor, which is same as this phasor. So this is V1 minus V3. The magnitude of this phasor will be root 3 times that of the phase voltage. So this is equal to 100 root 3. And this will be at an angle of 30 degree from P1. So this is at minus 30 degree in volt. Then we have to divide this by minus J to get I1. So let us divide it by minus J. So this vector will get rotated anti-clockwise by 90 degree. So this is 90 degree. This is I1. So it will have a magnitude of 100 root 3. And since this angle is 90 degree, this angle is 60 degree. So this is 60 degree in ampere. Similarly, let us find I2. I2 is given by V2 minus V3. So V2 minus V3 is this phasor, which is same as this phasor. So this is V2 minus V3. So the magnitude will be 100 root 3 and the angle is clearly minus 90 degree. This is in volt. Then we have to divide it by J to get current I2. So once we divide it by j, this phasor is rotated clockwise by 90°, and this is current I2. So the magnitude of I2 will be 100 root 3, and the angle is 180°. This is in ampere. Next, we have to add I1 and I2. You see, I1 and I2 have same magnitude. I1 is at an angle of 60° and I2 is at an angle of 180°. So the sum of I1 and I2, which will be here, so that will be exactly halfway between I1 and I2. So this is I1 plus I2, exactly halfway between I1 and I2. So the angle here, this angle is 120°. Okay, and how much is the magnitude of this vector, this phasor I1 plus I2? So for that, notice that this angle is 60° and this angle is also 60°. So the component of I1 along this resultant is 100 root 3 cosine 60°. 100 root 3 is the magnitude of I1 and cosine 60° is coming because the angle between I1 and the resultant is 60°. Then similarly, the component of I2 along the resultant is 100 root 3 cosine 60°. Again, so 100 root 3 cosine of 60°. So this is the magnitude of this resultant phasor I1 plus I2, and this is of course at an angle of 120°. So this is the value of I1 plus I2, and to get the current I, we have to put a minus here. Okay, so this is current I, and this will be equal to 100 root 3 minus 100 root 3 at an angle of 120°. That means basically this phasor opposite to I1 plus I2. So this will be equal to 100 root 3 at an angle of minus 60°. Okay, and this is in ampere. Ampere. So this is the answer. Now let us move to another question. Here we have a balanced three-phase supply, and we also have a three-phase balanced loading. Three inductors are connected in the form of a delta and three capacitors are connected in the form of a star. The value of the inductance is given here, 10 millihenry. We have to find the value of the capacitance, for which these line currents will all become zero. Okay, so one way to solve this question is to use a star delta conversion. So let us redraw this circuit. Here is the equivalent circuit. The inductors are kept as they were in the original circuit, L, L and L. However, the star formed by three capacitors is converted into an equivalent delta configuration, and suppose this new capacitors have capacitance of C prime each. Okay, then, and suppose these capacitors in the original circuit had an impedance of XC, and the impedance of these new capacitors in this modified circuit is suppose XC prime, then we know that XC prime should be equal to 3XC according to the rule of star to delta conversion. Now XC prime is given by minus J by omega C prime, the new capacitance, and this is equal to 3 XC. XC is minus J by omega C, the original capacitance. So from here we get C prime equal to C divided by 3. Now this equivalent circuit can also be drawn in the following way. So let me remove this wire and suppose I put a wire here and here. Okay. So let me rather draw it in this way, like this. Similarly, let me disconnect this wire and put the connections here, and same thing I will do here. So now we have a balanced loading again, and each load is a parallel combination of an inductor and a capacitor. We want these line currents all to be equal to 0. And since the load is balanced, the supply is also balanced. Therefore, these phase currents will also be balanced. So this, and these three currents are also balanced. Okay? And therefore, the line currents will be given by root 3 times of these phase currents. The magnitude of line current will be root 3 times of the magnitude of the phase current. Since the line current is 0, therefore the phase currents must also be equal to 0. All phase currents are 0. Okay. Therefore, now see that we have a voltage across this load, but the current is 0. That is only possible if the impedance is infinite. That means we need the parallel combination of this inductor and this capacitor to have infinite impedance. So we can write J omega L parallel minus J by omega C prime should be equal to infinity. That means the product of J omega L and minus J by omega C prime divided by J omega L minus J by omega C prime is equal to infinity. So the denominator here should be equal to 0. That means omega L should be equal to 1 over omega C prime. So omega L is equal to 1 by omega C prime. Okay, and that means C prime is equal to 1 by omega square L, and C prime is C by 3. So therefore C should be equal to 3 by omega square L. Now the value of omega is approximately 314 because the frequency is 50 Hertz. So 314 squared, and L is 10 milli. So multiplied by 10 and 1000 here. This is the value of the capacitor. Okay, so, and this is in farad because all quantities are in SI units. So from here we can write C is equal to 3 into 1000 divided by 314 squared into 10. This is in millifarad, which will come out to be equal to 3.04 millifarad, and that is the answer. Now we will move to the next question. In this question, we have a balanced star-connected three-phase supply and a balanced star-connected load, and the total power absorbed by this load is 432 watt. The line-to-line voltage is 208 volt. The power factor of this load is 0.6 leading, and from this we have to find out the value of this impedance Z. Okay, the complex impedance Z. So let me put a bar to indicate complex value. Okay, now we know that the power consumed by a three-phase load is given by root 3 VL line voltage, which is 208 volt, multiplied by the line current IL, magnitude of line current IL, multiplied by the power factor, which is 0.6, and this is equal to 432 watt. From this, we will get the value of IL, which will come out to be approximately 2 ampere. This is the magnitude of the line current or the RMS value of the line current. Since the load is star connected, therefore this is also same as the magnitude of the phase current, call that IP. However, the phase current is given by IP is equal to the phase voltage, which is 208 volt by root 3 divided by the magnitude of the impedance mod Z. Okay, and this is approximately equal to 2 ampere. From this, it follows that the magnitude of the impedance Z is approximately 60 ohm. And then the angle of this impedance, angle of Z bar, is given by cosine inverse 0.6, cosine inverse 0.6, and since the power factor is leading, that means the load is capacitive in nature, so this angle should be negative, and this is equal to minus 53 degree approximately. So therefore Z can be written as 60 with an angle of minus 53 ohm. That is the answer, and let's move to another question. Please read the question. Here we have a two-phase supply and a two-phase load. So we have two phases of the supply like this. Here is one phase plus minus, call it VAN, which is between the line A and the neutral line, which is here. And there is another phase of the supply, which is between phase B and the neutral. Plus minus, this is VBN. Then here we have a current IA, which is given here, and the current here is IB, which is given here. So therefore this current is obviously IA plus IB. Now we have to find the total instantaneous power flowing from the source to the load. Total instantaneous power delivered by these two sources. So that is given by, call it PT, instantaneous power, will be equal to VAN, which is of course a function of time, VANT, this voltage multiplied by this current IA, which is flowing through this source, IA. This is also a function of time, plus from this source we have the voltage VBN and a current of IB flowing through it. So VBN T multiplied by IB T. Now let us put the values of VAN, VBN, IA and IB as given in the question. So VAN is 220 sine 100 pi t. So 220 sine 100 pi t. This is VAN. Then current IA is given by 10 sine 100 pi t. So we have to multiply this by 10, and there is one more sine 100 pi t. So let me make it sine square. Then plus VBN is given here 220 cosine 100 pi t, and IB is given here 10 cosine 100 pi t. So multiplied by 10, one more cosine will make it cosine square, and this is in watt. Now sine square plus cosine square will become 1. So we will have 220 multiplied by 10. This is in watt. Next, let us go to the next question. Here we have a three-phase balanced supply. The phase voltages are given, VAN, BN and CN. These are all phasor voltages. And we have to find the value of R, this resistance, such that zero current flows through the neutral wire. So that means this current should be equal to 0. Now this current here is VAN divided by R. Then this current is VBN divided by J10, and this current is VCN divided by minus J10. If we add these three currents, then that will be same as this neutral current according to Kirchhoff's current law at this star point. So this should be equal to 0 since the neutral current is 0. From here we can write VAN is 100, so 100 by R, plus VBN is 100 angle minus 120 degree divided by J10, plus VCN is 100 angle minus 240 degree, that means plus 120 degree divided by minus J10. This should be equal to 0. This implies 100 by R plus second term is 10 angle minus 120 minus 90 is minus 210 degree plus minus 10 angle 120 minus 90 is 30 degree. This is equal to 0. Now minus 210 degree is same as plus 150 degree. From here we get 100 by R is equal to 10 angle 30 degree minus 10 angle 150 degree. Let us add these two phasors. Suppose this is a complex plane. Then we have 10 angle 30 degree, which is here, and 10 angle 150 degree will be here, but we have a minus sign, so we have to consider the negative phasor, so which will be here. So this has a magnitude of 10, this also has a magnitude of 10. This angle is 30 degree, this angle is also 30 degree. Therefore, the resultant, which will be somewhere here, that is equal to 10 cosine 30 multiplied by 2. Okay, so the right side is 20 cosine 30, that means 20 root 3 by 2, which is same as 10 root 3, and from here we can get the value of R equal to 10 by root 3, and the unit is ohm since all quantities are in SI units.